Okay, picture this. You show a computer a photo of a panda.
Right.
It's just a standard photo.
Uh-huh.
Cute, fuzzy, black and white, eating some bamboo. The computer analyzes it and says, that is a panda with 57.7% confidence. Not bad.
It seems perfectly reasonable. That's exactly what you want the AI to do.
But then an attacker comes along. They take that exact same photo and they add a tiny, almost invisible layer of static to it. And when I say tiny, I mean they multiply the noise by 0.007. To you and me, looking at the screen,
It's identical.
completely identical. It is still a panda.
But to the machine.
To the machine, it's now a given.
Yeah.
And not just a given. It is 99.3% confident that it's looking at a given.
That is the classic and frankly terrifying panda, to give an example from the Goodfellow and Jaha research. And it perfectly sets the stage for what we are unpacking today.
We're doing a deep dive into the world of adversarial machine learning. And look, this isn't just about tricking a computer for fun or making your smart speaker say something silly.
No, definitely not.
We are talking about the fundamental reliability of the systems you are starting to trust with your life. Autonomous driving, medical diagnostics, biometric security.
Exactly. The core conflict we found in this stack of research, from Jiha and Shirazi to Frank and Wang, it's this tension called the accuracy-robustness trade-off.
Which sounds super technical, but it is actually a really dramatic problem.
It really is. We are building systems that are superhuman at benchmark, like identifying images on ImageNet, but they are brittle. They shatter like glass when faced with these invisible changes.
So today we are going to break all of this down. We're going to look at how these attacks actually happen, specifically evasion and poisoning. We will get into the theoretical limits of whether we can ever actually fix this, looking at something called Bayes' error.
Which is fascinating.
It is. And finally, we will look at the arms race of defenses like distillation.
It's a bit of a detective story, honestly, but the detective is a mathematician.
I love that. Let's start with that, Panda. That is what's known as an evasion attack.
Right, and based on the Shirazi and Cha surveys, evasion attacks happen at test time.
So just to clarify for everyone, test time means the model is already finished.
Correct. The model is trained, it is deployed, ideally it's working. The attacker isn't breaking into the server to change the code, they are manipulating the input to force a mistake.
So how do they actually do that? How do you find the exact static pattern to turn a panda into a given? You can't just guess.
No, you can't. It all comes down to gradients.
Okay, let's unpack that. Because
Okay.
when I hear gradients, I think of high school calculus and I start to sweat a little.
Fair enough. Think of it this way. When a model learns, it's essentially trying to climb down a mountain to find a valley. The valley is the lowest point of error. The gradient is just the slope of the terrain.
Right.
It tells the model, steepness is this way, so go the other way to get the right answer.
So the model uses the map, the gradients, to
Yeah.
find the truth.
Exactly. But in an evasion attack, the attacker looks at that exact same map. But instead of trying to reduce error, they use the gradient to find the quickest path to maximize error.
Wow.
They ask, which pixel do I tweak, and in which direction to push this decision over the cliff?
That is devious. It's like using someone's own GPS to drive them into a ditch.
That is a very apt analogy. And technically, they do this using methods like the fast gradient sign method, FGSM, or projected gradient descent. But the logic is always the same. Follow the slope to the wrong answer.
Now, there are two ways to do this. There's the white box attack, like the Carlini and Wagner attack mentioned in the Jaha source.
That's where the attacker has the blueprints. They know the architecture, the parameters, the weights. They can calculate that gradient perfectly.
But what scares me more is the black box attack.
Okay.
This is where the attacker knows nothing. They just send inputs to the model, see the output score, and adjust.
This is the real-world scenario. You usually can't see the code of a proprietary security system.
But wait, if they don't have the map, the gradients, how do they know where to push the pixels?
This is where it gets really interesting, and honestly a bit unsettling. The JAS source discusses a phenomenon called transferability. It turns out different machine learning models often learn similar decision boundaries.
Meaning they make mistakes in similar ways.
Yes, they share the same blind spots.
So if I want to attack a secret model that I can't see, I can just build my own substitute model at home.
Exactly. You train your own model on similar data, you find the weak spots, the adversarial examples, on your model, and then you take those attacks and fire them at the secret target model.
And they work.
Surprisingly often, yes. The attack transfers. It's like finding a key that opens your front door and realizing it also opens your neighbor's door, even though the locks were made by totally different companies.
That is wild. And we aren't just talking about pandas here. The sources mention the stop sign scenario.
Right. Imagine a self-driving car approaching a stop sign. An attacker has placed a few specific stickers on the sign. To you, it just looks like a vandalized stop sign. You still stop.
But the car...
Because of that gradient manipulation we talked about, the car classifies it as a speed limit 45 sign and accelerates.
into an intersection.
Exactly. That is the real-world implication of an evasion attack. It exploits the gap between human perception and machine perception.
Okay, so that's tricking the model after it's built.
Mm.
But the Wang and Shirazi surveys spend a lot of time on a totally different vector. Breaking the model earlier.
Poisoning attacks.
Poisoning the well. This is where you mess with the training data itself.
Yes. The goal here isn't necessarily to trick a specific image later, but to degrade the model's performance generally, or install a backdoor.
A backdoor, like a sleeper agent in a spy movie.
That's a perfect metaphor. The model works perfectly fine for months. It classifies everything correctly until it sees a specific trigger.
Like what?
Like a yellow post-it note on a document or a specific pixel pattern in the corner of an image. And then it executes the malicious command the attacker taught it during training.
And this is particularly dangerous in something called federated learning. I saw this in the Wang source. Can you explain that setup?
Federated learning, or FL, is supposed to be better for privacy. Instead of sending all your data, like your text messages or personal photos, to a central server to train an AI, the training happens right on your phone.
Okay.
Your phone calculates the update and just sends the math back to the central server.
So the central server never sees my actual photos. That sounds great for privacy.
It is great for privacy. But for security, it's a nightmare. Because the server can't see the raw data, it has absolutely no way to verify if the update your phone sent is legitimate.
So if I'm a malicious client, I can send a poisoned update.
Exactly. And the Wang source distinguishes between data poisoning and model poisoning.
What's the difference there?
Data poisoning is just sending bad data, like putting a mislabeled image into the training set. But model poisoning, that is where you manipulate the gradients directly before sending them back. Yeah, in federated learning, since the server is just aggregating math model, poisoning is far more damaging. You are effectively rewriting the logic the global model is trying to learn.
And you can do damage with surprisingly little effort. The Shirazi source mentions label flipping. This is literally just telling the model that a dog is a cat in the training data.
You'd think modern algorithms would just filter that out as noise, right?
Yeah, I would assume the algorithm is smart enough to ignore the one guy calling a dog a cat.
But for support vector machines, SVMs simply flipping the labels on 40% of the data can severely degrade the model. You effectively confuse it into uselessness. It can't find a stable decision boundary anymore.
Okay, so we can trick them with evasion and we can poison them during training. Why is this so hard to fix? Why can't we just make better models?
This brings us to the theoretical heart of the problem. And for this, we have to look at the Frank et al. And Hosseini papers.
This is where we get into the Bayes area.
Right. In statistics, the Bayes classifier is the theoretical ideal. It's the perfect model. It makes the fewest possible mistakes given the underlying data distribution. It's like the speed of light limit for accuracy.
So you mathematically cannot get better than the Bayes classifier.
Correct. But the Frank paper introduces the adversarial Bayes classifier. This is the ideal model when you have an adversary who is allowed to wiggle the data around, perturb it within a certain radius, which they call epsilon.
And the problem is these two ideal models aren't the same thing.
Exactly. This is the conflict. The Frank paper shows that the decision boundary that gives you the best accuracy on clean data is fundamentally different from the boundary that gives you the best safety against attacks.
So it's a trade-off. If I want to be 100% safe against the Gibbon attack, I might have to accept that I'll be wrong about some regular pandas.
That is the accuracy-robustness trade-off in a nutshell. For example, on the CFAR-10 dataset, which is a standard image benchmark, standard accuracy is around 99%, but robust accuracy.
What does it drop to?
It drops to around 71%. You pay a steep price for security.
Now, you mentioned there was a surprise in the Hosseini paper, an aha moment regarding class balance.
Yes. I love this detail because it flips conventional wisdom on its head. In standard machine learning, if you have two classes, say cats and dogs, the hardest scenario is when they are perfectly balanced 50-50.
Because there's maximum uncertainty.
Right. If 90% of the images are dogs, it's easy to just guess dog and be right most of the time. But if it's 50-50, it's hard. However, Hosseini found that for the adversarial classifier, specifically in a binary Gaussian mixture,
Okay, keeping it simple for us.
yeah,
In a standard statistical setup.
in that setup, the natural error is actually locally minimized when classes are balanced.
Wait, so the thing that makes normal learning the hardest, a 50-50 split, actually helps with adversarial robustness.
It seems so. It completely contradicts our intuition for standard classification. It suggests that the geometry of robustness is fundamentally different from the geometry of accuracy.
That is counterintuitive. It's like saying driving in the rain is safer than driving in the sun.
In a way, yes. And the Frank paper also mentioned something about uniqueness. In normal learning, the perfect answer is usually unique. There's one best Bayes classifier. But they found that adversarial Bayes classifiers might not be unique.
Meaning there could be multiple correct ways to be robust.
Exactly. But they might have different levels of success on clean data, which gives us a sliver of hope. Maybe we just need to find the right, robust classifier that also happens to preserve clean accuracy.
Okay, let's talk about building the shield then. How do we defend ourselves? The forces mention a few strategies. The big one seems to be adversarial training.
This is the brute force approach popularized by Maidry and discussed in JAW. It's conceptually simple. You generate a bunch of those fake gibbons, put them in the training set, and tell the model, no, this is actually a panda.
You're inoculating the model. You're showing it the trick.
Ideally. But as Jaha points out, it is incredibly computationally expensive. You essentially have to attack your own model constantly during the training process. And as we discussed, it often lowers your overall accuracy on clean images.
Now, there was another defense that sounded really cool. Defensive distillation. This was in the paper, not source.
Yes. This uses a teacher and student metaphor.
Explain that. How does it actually work?
Normally, we train models on hard labels. This image is a 1 for panda or a 0 for not panda. But a model actually produces probabilities. Maybe it says 90% panda, 9% bear, 1% dog.
Those are the soft labels.
Right. In distillation, you train a student model not on the hard answers, but on the soft probabilities produced by a teacher model. You are effectively telling the student model, hey, this is mostly a panda, but pay attention, because it looks a little bit like a bear, too.
Why does that help with security, though?
It smooths the decision surface. Remember the gradient map we talked about earlier? The one with the cliffs?
The one the attacker uses to find the ditch.
Yes. Distillation effectively flattens that map. It reduces the amplitude of the gradients by a massive factor, up to 10 to the power of 30.
10 to the 30th power. That is massive.
It's huge. It means the attacker looks at the map and just sees flat land. They can't find the direction to push the input because the gradient is so microscopically small. In their study, it reduced the success of adversarial sample creation from 95% down to 0.5%.
That sounds like a silver bullet. We win.
Wow.
There is always a but. I can hear it in your voice.
There is. The JAW source warns about something called gradient masking. Distillation creates a false sense of security. It hides the gradient, yes, but it doesn't actually remove the underlying vulnerability.
It's like hiding the cliff with fog instead of building a fence.
That is a perfect analogy. If an attacker uses a black box attack, remember transferability.
They build their own model.
Right. They build a substitute model that doesn't have distillation. They find the cliff on their clear map. And because the cliff is actually in the exact same place on your map, you still fall off even through the fog.
So we are just back to the cat and mouse game.
We are. The Shirazi paper explicitly refers to this as game theory. Attackers find a hole with evasion. Defenders plug it with adversarial training. Attackers find a new way using transferability. Defenders try to hide the gradients with distillation. It just keeps going.
So what does this all mean for you listening, for the people who aren't necessarily building AI models in a lab, but are using them every day?
It means we need to fundamentally adjust our expectations. As AI becomes ubiquitous, in finance, in transport, in healthcare, we have to realize that accuracy is not the only metric that matters anymore.
Right. A model that is 99% accurate, but can be hacked by a strategically placed sticker on a stop sign, is not a safe model to put in a 2-ton car.
Exactly. Security is becoming a core dimension of quality. You wouldn't buy a car that goes 200 miles an hour but has no brakes. We shouldn't deploy models that are highly accurate but have zero robustness.
And what about that final thought from the Hosseini paper? You mentioned it earlier as a bit of a provocation.
This is what keeps me up at night in a good way. Hosseini shows that the theoretical gap between a robust model and an accurate model is actually very small. It's theoretically proportional to the square of epsilon.
In English for the rest of us.
Epsilon is that tiny, invisible perturbation we talked about at the start. Since epsilon is microscopic, epsilon squared is almost zero. It means that theoretically, it is mathematically possible to have a model that is both near perfectly accurate and near perfectly robust at the same time. The math allows it. We aren't hitting a fundamental law of the universe that says AI must be easily hacked.
But we just aren't seeing that in reality.
We aren't. Our current algorithms, the adversarial, training the distillation, they just aren't finding that optimal spot.
So we aren't hitting a wall in physics. We're hitting a wall in our own creativity.
Exactly. This raises an incredibly important question. Are we hitting a wall in how we currently teach machines to learn? The potential for a truly robust AI is sitting right there waiting. We just haven't figured out the right way to build it yet.
Now that is a fascinating place to leave it. We have the map. We just need to learn how to read it a whole lot better.
Ideally without driving off a cliff.
Ideally. That is all for this deep dive into adversarial machine learning. Thanks for listening, and as always, stay curious.